Okay, in this video clip, we're going to take one more look at this whole idea of leading clocks, lagging a trailing clock. So this is take 2. You may remember last time we did this derivation in terms of just looking at Bob. If he has a machine that gives off 2 photons, now Bob is on his spaceship. As far as he's concerned, he's at rest. As far as Alice is concerned down here, which we'll get to in a minute, he's going at velocity v from left to right. So on Bob's spaceship, he has a little device that emits 2 photons or light waves, and one goes toward his front clock and one goes toward the back clock. Or we'll say, to Alice's perspective, as Bob moves this way, this is the leading clock, and this would be the trailing clock or the front clock or the rear clock, however you want to specify them. And from Bob's perspective, remember, both of these light waves are going to hit his clocks at the same time, assuming that the device is right in the exact center of his spaceship. His spaceship has length L as far as he's concerned. And therefore, when the light beams hit each clock, they trigger a flash photo, take the picture, and therefore he sees both clocks as having the same time. Alice, however, remember, as Bob goes by here, the key fact is that she certainly sees the light beams go off in each direction, but because the speed of light is constant in all frames of reference, it means that she sees this light beam traveling at the speed of light c, and she sees this one traveling at the speed of light c, but Bob's leading clock is moving away from that light beam, and his trailing clock is moving toward that light beam. And therefore, it takes longer for the light beam going toward the leading clock to reach that and trigger the flash photo versus the one going backwards to the rear clock and triggering that flash photo. So on Bob's clocks, when the flash photos are triggered, both of them show, both these photos, one here and one here, show his clocks having the identical time. But in Alice's clocks down here, again, remember the lattice of clocks that we always have to imagine in any frame. Bob also would have a whole lattice of clocks, but we only need 2 for this case. So imagine Alice's lattice of clocks all synchronized in her frame, just as Bob's clocks are synchronized in his frame. And we can see just qualitatively, and we argued this a while back, that again, as far as Alice is concerned, even though Bob's 2 clocks, the photos indicate the flashes hit at the same time, as far as she's concerned, they aren't synchronized because she sees this flash occur after that one. And so, to Alice's perspective, she sees this flash occur, records the time there, and she can compare it to her clock here. They'll take the same flash photo of both clocks at that instant in space and time. And then a little while after that, she would see the light beam hit Bob's front clock, the leading clock, and she'd record a time for that as well. So that this clock, to Alice's perspective, is ahead of this clock, or this clock lags this clock, because Alice, as far as she's concerned, her clocks are synchronized. It's Bob who has a problem with the synchronization of his clocks. And so we capture that idea in the phrase leading clocks lag, that this clock on the leading edge of Bob's spaceship lags behind this clock as far as Alice's observations are concerned. And so last time we sort of worked our way through a derivation of that because we wanted to do it quantitatively. We wanted to actually get a result that we might be able to use in certain cases. And so we found that result was, to Alice now, that the difference in Bob's 2 clocks was, in general, a distance d, which here was the length L. But in general, it's going to be a distance d between the 2 clocks. We're talking about the velocity, the relative velocity between the 2 frames, Alice and Bob here, and then the speed of light squared. So that was the result we came away with after a little bit of calculation. By this point in time, especially after our last few video clips, you might be thinking, that these are getting a little long here in terms of the calculations we have to work through. But first of all, remember that it's just a little basic algebra. Once we sort of get the situation set up and analyze it, then we just work our way through the end. And if it helps, there's a nice quotation from Einstein, the story goes, he was at a dinner honoring him as a National Academy of Sciences dinner, and sort of halfway through listening to the speeches honoring him, he turned to his companion and said, "I now have a new theory of eternity," obviously referring to the long-winded speeches that have been going on. So maybe you feel like that a little bit as well, going through some of our analysis here, that it seems to take an eternal time to get to the end. But once we get to the end, and again, the analysis, we're not doing anything too fancy in terms of the math involved, but just some basic assumptions, principles that Einstein started off with, and then we're following them through in certain instances to see what the conclusions are. And one of the startling conclusions, or the weird conclusions we get, is that when a spaceship like this is traveling by, it's got two clocks, one at either end, or just any moving clock. So you could have a clock way out there and a clock way over here. In terms of Bob's lattice of clocks, Alice would see it in terms of her synchronized clocks as a time difference dv over c squared. Now note here that this is going to be a very small number in practice, and it's why we don't see it in common everyday life, because we've got a c squared on the bottom, a huge number, and only a v on top here, and the d. And normally the distances involved are much smaller, even when you multiply distance times velocity, much smaller than the c squared here. So in general, this is a very small number, but when you get up to speeds near the speed of light and large distances, then this can have some interesting effects that can be observed, and we'll talk about that a little bit later on in our course. What we want to do now, though, in terms of take two, is use our Lorentz transformation to get this result much more quickly than we did before. As an example of the power of the Lorentz transformation, remember where we got it from. We used the invariance of the interval, and time dilation came in along the way, and so on and so forth. But once we get to the end of it, based on those basic principles, then we have this tool we can apply in situations like this. So we don't always have to go back to sort of first principles and basic situations to get an answer that we might want. So let's see if we can apply the Lorentz transformation to this situation and get our dv over c squared result, or lv if we're using the length L for the spaceship here. So let's just modify this slightly. So we're not going to use the light beams anymore here, or the photons if you want to call them that. So we're just going to look at Bob's ship, and let's actually label the clocks here so we know what we're talking about. So this will be clock, say, B1, and this will be clock B2, and I didn't quite line them up nicely here, but we'll say this is Alice's clock A1, and we're going to assume it's lined up with Bob's clock there. And then we also have Alice's clock A2 over here. Okay? So the question we want to ask is, but before we get to the question, let's just say this. Let's also set, remember, the Lorentz transformation, the basic equations are, we have two equations. One is T sub A for Alice is going to equal gamma. These are the time. This is the time equation now. Gamma times T sub B plus V over C squared x sub B. In other words, given the space-time coordinates, the x coordinate and the time coordinate of something happening in Bob's frame, according to Bob's measurements, his time and distance measurements, then I can find out the time coordinate in Alice's frame given this equation here, where gamma is our usual factor, 1 over the square root of 1 minus v squared over c squared, and v is the relative velocity between the two frames. So that's one. If we wanted to go the inverse transformation, say we were thinking about if we were given Alice's coordinates, and I wanted to find something, a time for Bob on one of his clocks, it'd be gamma T sub A minus v over c squared xa. So remember, as we said before, usually it's best to sort of memorize one form. If you use it a while, you'll just get it down. And then remember, the inverse form is just the negative factor. So usually we try to remember the form where, okay, we've got Alice stationary, Bob moving with velocity v left to right, and then this equation here applies, and then we can just reverse everything, sort of, and get this form. And of course, there are comparable equations for XA and XB. We're not going to use them for this analysis because we're just dealing with the clocks. So we know what those two equations are. Let's remember that these equations apply when we have a reference point. In other words, at some point where we say, okay, this is time A was 0, to Alice was 0, time for Bob was 0, X position was 0, the X location, and the X location, well, for both of them, Alice and Bob. And so let's just assume for our analysis here that clock A1 is at TA1 equals 0. When we take a flash photograph of it, it's reading 0. And we'll also assume in that flash photograph, time for B1 equals 0. And we can set things up that way, of course. It's just one flash photograph there. We can have our clocks set however we want them. Remember that as far as Alice is concerned, all her clocks are synchronized, and all Bob's clocks are synchronized as far as he is concerned. So we'll do that, and we'll also assume, of course, that this is maybe our 0 point, that XA equals 0 here and XB equals 0, right at that instant as Bob passes by Alice, and the two clocks B1 and A1 line up. Okay, so we've set that up. So clearly this is the leading clock here. B2 is the trailing clock. And the question is, we take this flash photograph. Let's also, at that instant in time, take a flash photograph back here. So because, and this is from Alice's perspective, because all her clocks are synchronized, she'll see this, TA2 equals 0. Okay? Those flash photographs both show her clocks reading 0. That's why we know it's from Alice's perspective, because if this reads 0 and this clock reads 0, we know they're synchronized. We know they're at the same instant in time as far as Alice is concerned in terms of readings from her clocks. So we also know for the first flash photograph, TB1 equals 0 here. The key question then is, what does TB2 equals what? That's what we'd like to find out. And ideally, we'd like to see that if this is TB1 equals 0, and we just did the other derivation that leading clocks lag by an amount dV over c squared, we're hoping to get that dV over c squared factor for this trailing clock, or LV over c squared, since we're talking about a length L between them, or distance d if we want to call it a distance. Well, let's see what we can do with this. We're after a time in Bob's reference frame, so let's use the TB equation here. Okay, so just start off from this one, and we can say, okay, we've got TB2 equals what? This is what we're after. Given this situation here, flash photograph, at the same instant as far as Alice is concerned, this reads 0, this reads 0, this reads 0. What does this clock here read? The Lorentz transformation will give it to us. So we've got TB2 equals gamma TA2 minus V over c squared x A2. So if we know what TA2, the time on Alice's second clock, and we know the position of Alice's second clock according to Alice, then we're good to go here. Well, let's take a look at this. So clock TA2, here we are, sorry, right here, is 0. We've set it up that way. And so this is just going to equal gamma times 0. We set our situation up that way. There are other ways we could set this up. Essentially, we'd get the same answer. So we know it's 0 minus V over c squared. Now, what is XA2 here? What is the position, the X location, as far as Alice is concerned, of her clock A2? Well, the only distance we have involved here is the length of Bob's spaceship, according to Bob. And remember, to Alice, that length is contracted. It's shorter. And so what we have for her length, really this position here, if this, remember, is position right here, is XA1, equals 0. We just set our 0 point there. Then this is in the negative direction. And in fact, it's going to be minus L over gamma. Okay? That's the distance between those two clocks as far as Alice is concerned. So let's see what we have. We plugged in our numbers. Okay, remember we're using the length contraction factor there for that distance, because again we're given length L in terms of Bob. And so this just becomes gamma. And inside here I've got 0 minus, and I've got a negative v over c squared times a negative L over gamma. The negative signs cancel, so I get a positive. So I get v L over c squared gamma. And then we can see the gammas cancel, and we get, we'll switch the order of the L and V. We get L V over c squared. In other words, the same result we got previously, although it took a lot longer previously to get it. So it shows the power of something like the Lorentz transformation. Once we have that tool in our toolbox, then we can apply it to situations like this, so we don't always have to go back to sort of the first principles and get the answer we want. So that's take 2 on leading clocks lag. So remember, first of all, that leading clocks lag. So when you have a situation where a set of clocks is moving past an observer, then that observer, for any 2 clocks in the set that are moving past, the distance between them in the clock's frame, in this case Bob's frame, so that'd be L here, but it could be, it doesn't have to be the length of a spaceship. It could just be 2 distant clocks encoding to Bob's lattice of clocks, times the velocity over c squared. The leading clock will lag the second clock, the trailing clock, in whatever situation you're looking at there. So that's another derivation of that. Hopefully that gave you a little more insight into not only just the LV over c squared factor and a reminder of how this all works, but hints a little bit at the power of the Lorentz transformation and how we can use it in situations like this. And the key thing really is to use the correct equation, then think how things are set up here and get the right values in there, and then hopefully, of course, get the right answer.